Okay, so in this question, we're considering a collision between a driver of a car and a wall. So let's draw a little diagram showing the situation. So initially we've got our driver coming in towards the wall here. He's got an initial speed of 70 meters per second, and he hits at an angle of 30 degrees below the horizontal, and then he bounces off the wall. So he comes off over here. This is 10 degrees, and the final speed is equal to 50 meters per second. And in the first part of this question, we're asked to calculate the impulse. So we know that the impulse is equal to the average force times the time, and it's also equal to the change in momentum. Now in this case, we do know the mass of the driver. The mass of the driver is equal to 80 kilograms. So what we can actually calculate is the change in the momentum, because we have the initial velocity and the final velocity. So let's go about and calculate the change in momentum. So to do that, we'll want to work out the initial velocity and then the final velocity, and we'll break it into x components and y components. So here's our x component, here's our y component. So let's put initially, we've got vx initial, and so splitting this into two components, let's change colors. We can have our, let's call this one uy, and then we've got along here ux, and so this thing here is our ux, and we can see here this is adjacent to the 30 degrees, so this is going to be 70 times cos 30. Then if we want to get the initial momentum, we can say, well, p initial x is going to be equal to the mass times this. So that'll be 80 times 70 times cos 30. And solving that, we have 4,850 kilogram meters per second. And this is to the right. And then we want to do the same thing vertically. So Vy initial is equal to Uy, which is this one. And so we can see this is the opposite angle. So this will be equal to 70 sine 30. So then to get the momentum, the final Y momentum, it's the initial Y momentum, we just multiply this by the mass, which is the 80 kilograms. So we've got 80 times 70 times sine 30, which when we solve it on the calculator, we get 2,800 kilogram meters per second, and that is towards the wall, so up. And then we need to repeat this for the final momentum. And so we'll want px final. And so here we can split this velocity again into an x component and a y component. So here we've got vx, here we've got vy, and so px final will be m times vx final, which will be 80 kilograms times the x component. Now this is adjacent to the 10 degrees, so this will be times 50 times cos 10. And solving that, we get 3,939 kilogram meters per second, and that is still traveling towards the right. And then we want to find the final y momentum, so we want py final, which is equal to m times vy final. So we're trying to work out this one here, which is opposite the 10 degrees. So that's the mass, which is 80 times 50 times sine 10, which is equal to 694.6 kilogram meters per second. And in this case, it's traveling downwards. Okay, so now we're going to calculate the change in momentum. So we'll do that in the x direction and then in the y direction. So the change in momentum in the x direction is equal to px final minus px initial. So px final is equal to 3,939 kilogram meters per second to the right, and then we're subtracting off 4,850 kilogram meters per second to the right, and so that is equal to minus 911 kilogram meters per second to the right, which we can also write as 911 kilogram meters per second to the left. Now, to calculate the change in momentum in the y direction, we're going to want the final y momentum minus the initial y momentum. And so this is equal to 694.6 kilogram meters per second downwards minus 2,800 kilogram meters per second up. So to switch this from going up to down, we can make it positive and make this down. So summing these together, we get 3,495 kilogram meters per second down. So to get our impulse, we're going to want to know our change in momentum as a vector. So to do that, we can add our 3,495 down to our 911 to the left, and our resultant vector is here. We can call this angle in here theta. Now, to get the magnitude, we'll need to use Pythagoras' theorem. So this is got a magnitude of 3,495 squared plus 911 squared. When we add those and take the square root, we end up with 3,611, which is equal to 3,600 to two significant figures, and that's kilogram meters per second. And then because it's a vector, we're going to want a direction, so we'll need to work out what this theta is. So to get that theta, we can say, well, tan theta is equal to opposite, which is 911 over adjacent, which is 3,495. So taking the inverse tan of this thing tells us that theta is equal to 15 degrees. So this tells us that our impulse is 3,600 kilogram meters per second at an angle of 15 degrees to the left of vertically down. And then in part B, we're asked to calculate the magnitude of the average force. So to do that, we'll be using this part of the impulse equation here. So we've got that the magnitude of our average force is going to be equal to the magnitude of the impulse divided by time. And so this is equal to 3,600 divided by the time of the collision, which is 14 times 10 to the minus 3 seconds. So this is equal to 2.57 times 10 to the 5, which is equal to 2.6 times 10 to the 5 newtons.